Swayam Prabha. Digital India. Educated India.
What about other engineering properties? Modulus of elasticity of concrete is also important because it governs the ability of concrete to resist deformation. Okay. So, usually it is not tested directly, but there are of course test methods, and it is usually recommended that for any special concrete you should be testing the modulus every time. Nevertheless, in most cases what we do is we use code prescribed relationships that link the modulus to the compressive strength. So, as per IS 456, which is the code for plain and reinforced concrete construction, your modulus E in megapascals is given as 5000 times square root of FCK, where FCK is the characteristic compressive strength. Remember, I talked about the grades M30, M40, etc. When you say something like that, this 30 and 40 are nothing but characteristic compressive strengths. Okay. As I said, I defined what that strength means in terms of specimen size, in terms of age of curing, type of curing and so on, but I did not get into the statistics behind it. So, there are statistical considerations also behind defining characteristic strength, but again that is not a subject for us to discuss in this course. In most concrete, your modulus will be between 15 and 40 gigapascals. Of course, the higher the strength, the greater the modulus. Okay, and your Poisson's ratio typically will be between 0.15 and 0.22, more or less an average of about 0.18 to 0.2. Okay, experimentally you can measure the Poisson's ratio by measuring the elastic modulus and shear modulus and applying this simple elasticity equation where nu is equal to E by 2g minus 1. Now, one important aspect that we need to consider beyond the loading criteria is the ability of the concrete to withstand its service environment. So, concrete basically has to function very well in the environment of service. If you have a coastal zone, obviously you have the chlorides from the marine environment which may affect the properties of the concrete by corroding the reinforcing steel. So, how does concrete survive in a given environment? So, durability is the term that we use to define that aspect. So, again, according to the American Concrete Institute, ACI, the durability of hydraulic cement concrete is defined as its ability to resist weathering action, chemical attack, abrasion or any other process of deterioration. So, again, all non-load related processes are related to the durability of the concrete. Okay. Again, durable concrete will retain its original form, quality and serviceability when exposed to the environment. That means all these aspects will be negatively impacted if you have a problem of durability of concrete. Interestingly, all durability problems such as corrosion of steel in reinforcing concrete, chemical attack of concrete, alkali aggregate reaction, remember we talked about this when we talked about the aggregate type, and then freezing and thawing damage. Okay. When we talked about air entrainment, we talked about freezing and thawing damage. So, all these problems interestingly are related to the presence of water. If water is present, all these problems will happen. If water is not there, you can avoid many of these problems. So, generally durability is intrinsically linked to the permeability of the concrete. How easy is it for water and other aggressive chemicals to enter the concrete? Okay, because of that, durability is intrinsically related to the water tightness of the concrete or the permeability of the concrete. If you can avoid water and other chemicals from getting into the concrete, you will avoid many of the problems that concrete has. The other aspect that governs the long-term performance of concrete, one is of course the structural aspect, the loading. Second is the durability, that is a response to the environment. The third is what is called creep and shrinkage. Now, please remember, when you do a test in the lab, it is only for a matter of few minutes, but a concrete standing in a structure, concrete in a column which is in a structure, is being subjected to load for many years. Okay. Now, compare this to yourself. Let us say you lift a bucket and put it down. Second case, you lift that same bucket which is full of water and keep it for a very long time. Keep it held up for a very long time. What will happen? Obviously, your body or your hand will feel the strain of lifting the bucket a lot more than it felt when you just lifted it for an instant and kept it down. That basically is the response to sustained loading, and we call that as creep. Creep in concrete, although it's not as much as polymers, which we'll talk about in another chapter in this course, creep is not that much as in polymers, but creep can affect significantly the properties of concrete. Okay, when you have creep, it can lead to a faster rate of degradation or deterioration. They can increase the strain levels in the concrete. Okay, the other aspect is concrete has water in it, and this water can dry out of the concrete, causing volumetric contraction, and that is called shrinkage. Now, if you have a piece of concrete that is floating in space and it's drying, nothing will happen to it. It will just keep reducing in size. But if the same piece of concrete is held inside a structure and it wants to shrink, the structure will not allow it to shrink because there are restraints to its shrinkage. You cause restraint to the movement, and because of that restraint, you will get cracking. Okay, similar to a slab sitting on the ground. Okay, so if the slab wants to shrink, the ground basically restrains it from moving, and that restraint will cause a shrinkage. So, restraint causes cracking in the case of shrinkage. Okay. Now, in some cases, of course, creep and shrinkage can act in opposite directions, which may offset the damage to some extent. However, you have to still consider and understand the individual effects of these. Okay. As I said, creep in concrete is much lower than creep in polymers, but usually it's much greater than that in metals, especially steel. So, you want your concrete to be strong, yes. You want your concrete to be durable. You also want your concrete to be dimensionally stable. That means it should not change its volume with time. And this time dependent change in volume is caused typically by creep and shrinkage. Now, interestingly, the factor that affects the creep and shrinkage most is the amount of aggregate. More the aggregate, more the stability. Okay. We took to construction with concrete as compared to construction with stone because we had this magic ingredient, that is cement paste, which could help mold the concrete in any shape we wanted. But it turns out the cement paste is the reason why the durability or dimensional stability problems actually occur. The aggregate for the most part is inert and does not do anything, and the more the aggregate that is there in your system, the more stable your system is going to be. Okay? So, please keep that in mind when you design concrete. Although we want cement paste to be the primary factor governing the behavior of the concrete, we want as much aggregate there as possible. Okay? That is what we need to consider while designing concrete, and it also makes the concrete more economical that way. Now, we talked about concrete separately. In another chapter, my colleague Professor Pillai would have talked about reinforcing steel, or will be talking about reinforcing steel. But let us talk a little bit about steel concrete composites. Of course, reinforced concrete itself is a composite because it's got steel reinforcement inside a concrete structure. But we can also have special composites of concrete and steel, like hollow steel tubes that are filled with concrete. Okay, there are special advantages there because when you fill up concrete inside hollow steel tubes, you're saving a lot on steel as far as compression members are concerned. Secondly, the concrete prevents the steel wall, which is thin, from buckling. And third, the steel which is confining the concrete inside increases the load carrying ability of the concrete. Remember, we talked about the fact that when you compress a cube, you're basically causing it to bulge outwards. So, if you have a concrete which is confined in the steel tube, the compression of the concrete will be resisted by the tube and it will cause the confinement, and that confinement increases the load carrying capacity. So, these are called hollow steel tubes filled with concrete. Okay. So, that is one way of establishing another composite relationship that is much better than what you would have if you just had a concrete column or a steel column. The other way to use steel concrete composites is what we call as pre-stressing. Now again, just taking the simple example of a beam here. So you have this beam which is loaded from the top, and that top loading results in a deflected shape which is like this. Okay, beam basically deflects, and while it's deflecting, there's tension at the bottom and compression at the top. So the concrete will basically fail because of this tension. Okay. Now what do? We put reinforcing steel to take care of this tension. But can we do something else? And that's the essence of pre-stressing. So what we do here is we put a steel rod inside. Okay, we put a steel rod inside which is of very high strength. We pull the steel rod. While we pull the steel rod, we apply a compression reaction to the concrete. So you hold against the concrete and pull the steel rod. So you are applying a reaction to the concrete. So the tensile force that you apply in the steel rod is balanced by the reaction which is compressive in the concrete. So you are causing compression of the concrete. Pre-compression is being caused to the concrete. So when you have the steel rod below the central axis of the concrete and you are applying this tension to the steel rod and compressing the concrete, what you will end up doing is causing the concrete beam to bend upwards. Concrete beam will bend upwards. So this downward bending is called sagging. This upward bending is called hogging. So now what is going to happen? This concrete beam, even before it's actually loaded in the structure, has now bent slightly upwards. Now when you take this and put it in the structure and you subject it to load that's coming from the top, what will happen? The net result of this deflected shape that is upwards and the deflected shape that is expected from the loading that will be downwards, the net effect will be 0. So your net deflected shape will be perfect. Your net deflected shape or net deflection will be 0. So what you are doing is you are cheating the concrete into believing that it's not experiencing any tension, right, by causing it to compress before it's getting loaded. So you have a pre-compression that causes compressive stress throughout the concrete. Then you have the loading in the structure which causes tension at the bottom. So the compression because of pre-compression and tension because of loading cancel each other out. Okay. So pre-compression is applied to concrete to overcome tensile stresses due to loading. There are different types of pre-stressing. It depends on when you apply this stress to the steel. Okay. Of course, the steel which is used in this case is not the same as a reinforcing steel. I'm sure that you'll learn more about it in your steel chapter with Dr. Pillai. Okay. These are called high strength strands. So you have individual strands here, you can see, and usually these strands are bundled together. So in this case you have a 7-wire strand. Sorry, you have high strength wires which are bundled together to make a strand. So this is a 7-wire strand, okay, which is bundled together, and then you produce a certain length of this steel. Okay. So these strands are the ones that are going to be stretched in a pre-stressed concrete member. So if the strands are stressed before you pour the concrete, we call it pre-tensioning. If the strand is stressed before the concrete is poured, we call it pre-tensioning. I'll come to an explanation in just a minute. However, if you prepare the concrete that hardens and then you prepare it with some sort of a cavity inside and then push the strand inside and pull it to cause compression in the concrete, that's called post-tensioning. So pre-tensioning means that you have the strand sitting inside fresh concrete and concrete hardens around it. Okay. Post-tensioning means that the steel is actually embedded only after the concrete hardens. Okay. So how does this work? So let's take the example of pre-tensioning. So these are the end blocks through which your steel is stretched in tension. Steel is getting stretched in tension through the end blocks. Okay. Now you pour the concrete. So concrete is poured, right? The steel is not going to transfer any stress to the concrete if it is in the same stretched state. But what happens if I cut the steel here? That's what is done here. If I cut the steel here, what will happen is the steel which is elastic will want to go back to its original dimension. So, when it wants to go back to the original dimension, it conveys a compression to the concrete. It conveys a compression to the concrete and results in this sort of a shape which we call as hogging shape. So, that is called a pre-tensioning, right, that is called a pre-tensioning. So, you can see here, this is the end block, this is the steel bars that have been stretched through the end block, this is the formwork, and the concrete is basically poured inside. And after the concrete attains some level of strength, okay, because if the concrete is fresh and then you cut the steel, nothing will happen, right, it is not going to transfer any stress. The concrete has to gain some strength, concrete poured and then gains some strength, and then you cut the strands. When you cut the strands, it transfers the compression to the concrete, okay. And with this, we actually usually make a lot of beams for bridges, like the ones which are shown here. These are called girders, and you can see these are the steel strands that are running through the concrete that have been cut, and that has transferred pre-compression to the concrete, okay. What about post-tensioning? Post-tensioning is what you see commonly in your segmental bridges. I had shown you an example in the first part on the concrete lecture. So, your segmental bridges are here, right. So, these segments are basically transported to the site. After casting at the factory, these segments are transported to the site, taken and then stitched together. It is almost like stringing beads, right. You take beads and put them in the string and tighten the beads against each other. That is what you are trying to do here. So, you have several of these segments which are put against each other. You push the pre-stressing strand through it and then stretch the strand, passing the compression onto the pre-stressed members, and that is what is basically shown here. This is again an end block showing where the strands are actually coming out, just like what is here. It is a magnified view of what you see there, okay. So, you cast the concrete with a duct inside. Concrete is cast with a duct inside, so that you can push the steel through this duct easily. The problem is, after the pre-stressing has been done and the compression has been transferred to the concrete, the steel is freely sitting inside the duct, and if you leave it like that, it will corrode with time, and corrosion obviously will lead to a rapid loss in its tensile capacity. So, what you need to do is fill up the duct filled with grout after completion of work. After completion of stressing, the duct is filled with grout, and that causes the steel to be protected against corrosion, okay. So, now here this is a case where they are actually post-tensioning slabs, and if you go to many of the multi-story buildings today, to avoid too many columns and have very large open floor areas, they go for post-tension slabs, PT slabs, very commonly seen in many of our construction sites today, okay. Post-tension slabs are commonly used today, okay, but mostly you will see post-tensioning applied extensively in bridges today, okay, like the pedestrian bridge that is shown here, or the metro rail bridge that is shown here. This is a Chennai metro rail construction project where they have these segments basically launched and sitting against each other. Right. So, with this we come to the end of the chapter on concrete or cement and concrete. Throughout this chapter, one thing that would have come across very clearly is that concrete is a very versatile material. It is easy to apply and it is long lasting, provided you do a good job of the construction. It is very critical to do concrete construction properly to ensure that you get the best effects or best results out of it. Proper application of the concrete ensures a long life of the structure, and that requires a thorough understanding of the ingredients and their effects. And as I said, apart from the structural engineer, apart from the contractor, the site engineer and so on, you need a concrete technologist who is a specialist who understands the properties of concrete well on a job site to ensure that the concrete is applied properly, okay. And today, of course, we are increasingly dealing with special composites of concrete with steel, one of which is the pre-stressed concrete. And without pre-stressed concrete, a lot of our structures would have been very difficult to make with just reinforced concrete. Okay, so you need to remember that advancements in concrete basically deal with application of new and different types of composites which can be made with steel and concrete. Right. So, with that we come to the end. There are several websites which have information in concrete. Understandingcement.com is a very useful website. This website is my own, that is www.theconcreteportal.com. But of course, much of the information that is presented here has a lot of detail about concrete. You don't need to get to that to this course. Okay. Of course, for this course, textbooks that you may want to refer to are Mamluk and Zanussi and P.C. Varghese. Okay.